All right, so 154, we're looking at shortcut conversions, which work between binary and octal and also binary and hexadecimal. And that has to do with the fact that both 8 and 16 are powers of 2. So we can use the shortcut technique. That would also work if we were working with like base 3 versus base 9 or 27, or let's say at base 5 and you wanted to convert it over to base 125, right? Because 125 is a power of 5, that would actually work, all right? But just a little bit on the theory behind it. When you have a binary number, right? Binary numbers are, I'll just write it over here. Made up of zeros and ones, right? If I have a single binary digit, so one binary digit, which is known as a bit, that could be a 0 or a 1, right? If I have two binary digits, you could have anything from 0, 0 to 1, 1. All right. Now, the place values associated with a 2-digit binary number would be 2 to the 0th, 2 to the 1st. All right. And regardless of what the place values are, anything times 0 is 0. So you'd have 0 plus 0, which would be equal to 0 if we were going to base 10 or decimal. All right. Here, I'd have 2 to the 1st, 2 to the 0th. So 2 times 1 is, no. 2 times 1 is 2. Plus 1 would give me a 3. All right. So going from 0, 0 to 1, 1 in decimal form would be 0, 0 to 1, 1 in binary form would be the same as going from 0 to 3 in decimal form. All right. So 0 to 3, that's 4 digits. All right. So you could actually make a case that that's the same as going to base 4. All right. If we were to work two binary digits at a time, each pair of binary digits would be equivalent to a single base 4 digit. All right. If I had 3 binary digits, it's pretty clear at this point that I struggle with that word. All right. 3 binary digits, 0, 0, 0 to 1, 1, 1. The place values would be 2 to the 2nd, 2 to the 1st, 2 to the 0th, right? Which really amounts to 4, 2, and 1 if you want, right? So, but I'll write it as 2 to the 2nd, 2 to the 1st, and 2 to the 0th. So still equal to 0 over here. On this side, you would have equal to 2 to the 2nd is 4, plus 2 to the 1st is 2, plus 2 to the 0th is 1, and that gives you a result of 7. So that's going from 0 to 7, which is 8 digits, which is what the octal system is made up of. And if I go 4 binary digits, that would get me as far as 16 digits. I'll show that in a little bit, but for now we'll focus on the binary to octal. All right. So the way we handle it is by taking, so I'm looking at example 1, taking our binary number, which has, I think in this case, 8 digits to it, and we split it up into groups of 3. We're going to essentially convert each group of 3, each string of 3 binary digits over into octal, a single octal digit, by multiplying by 4, 2, and 1. All right, again, That's the same as saying 2 to the second, 2 to the first, and 2 to the 0th. All right. So we're going to do that across the board. But then, in the last one, you're like, oh, but there's only 2 values. Well, we could, to make ourselves feel better, I guess, we could throw a placeholder value in there. It's going to zero out anyway. So it really doesn't make much of a difference one way or the other. But I can at least see the consistency now. All right. So 4 times 0 is 0, plus 2 times 1 is 2, plus 1, result 3. 4 times 1 is 4, plus 2 times 1 is 2, plus 0 gives me a 6. Then 4 plus 0 plus 1, result 5. So that's going to be in octal 365. Right? And that's what all of this gets at here. All right? So going the other way is really just a matter of taking each octal digit and working backwards by seeing how we can group together zeros and ones in such a way that we can get to that, whatever the target number is. All right. So looking down here, I have 274, and I want to put that in binary. I would look at the 2, the 7, and the 4, knowing that I'm using powers of 2, which is, again, 2 to the second, 2 to the first, 2 to the 0th, which amounts to 4, 2, and 1. You make a little table out of it if you want. Some people are really good at doing this in their head. For most cases, just seems like a better idea to write it out just to make sure you don't make any careless errors. But yeah, if you come up with or if you like an organizational strategy that works for you, you wouldn't have to do it this way. But this is an option. I'll put it that way. Now, what I want to do is get to this target number of 2, and I want to do that with essentially mixing and matching 4, 2, and 1, right? Knowing that I can only use at most 1 of each of those values. So if I want to get to a target value of 2, I can't use a 4, that's too big. I can use a 2. I can't use anything more than that. I've already reached my target number, so I don't need a 1. All right. If I want to get to a 7, I would need a 4, right? If I didn't have 4 as an option, I would need more than 1, 2. And since I can only use at most 1 of each value, I'd have to use a 4. I'd have to use a 2. That gets me to 6. And then I would have to use a 1, getting me to 7. All right. And we discovered earlier that 111, which is the largest 3-digit binary number, amounts to 7 in decimal, right? And 7 in decimal and 7 in octal, you're looking at the same place value. All right. For 4, I would just need one of the 4s, and I'd be good. You just got to be careful because some people will say, well, why don't I just take 2 of the 2s? But then you got to realize, again, it's binary, so you only have choices between 0 and 1. And they'll say, well, 2, binary 2, that seems to make sense. But remember, our lowest number is 0. If I went up to 2, that would actually be 3, or a base 3 number. All right, so I want one of the 4s, which would get me where I need to go. So I'd be looking at 0, 1, 0, 1, 1, 1, 1, 0, 0. That would be in base 2. Now, we tend not to lead off with a 0 just because it doesn't amount to anything anyway, so I would just drop that off. If you left it on, it wouldn't be a big deal. It's really more of an issue if you forget like a 0 on this end, because then everything gets slid over a place value. But if you forget it on the left side, it's okay. It would be kind of like if I were to say, for example, the number was 0, 1, 0. And let's say it's decimal. Like I'm in like a 3rd grade math class, and I accidentally wrote 0, 1, 0. and the teacher took off a point on the test or something. You're like, but it means the same thing, right? As opposed to, so this is the same as 10. Now, if I had, let's say I wrote a 10, but I meant 100 because I forgot to put a 0 over here, that would be a problem because that extra 0 on this side actually represented a place value that was significant. It wasn't significant over here because it didn't impact the value of the number, but in this case it is. So we got to be careful about that, but in this case it's fine, all right? And so that's where this, slight miss there. That's where this number comes from. All right, so going 351 from octal to binary, so 3, 5, and 1. Again, working with only 3 values, 3 binary numbers. The place values are 4, 2, and 1. It would be too much if I had a 4. If I have a 2 and a 1, 2 plus 1 is 3, so that's good. All right. To get to a 5, I need a 4. But if I take a 2, that gets me to a 6. That's too much. So I'll just take a 1. And to get to a 1, I don't need a 4, I don't need a 2, but I do need a 1. And again, strike that first value, and we would get, well, it's down here, but I'll write it up here anyway. So 0, 1, 1, again, striking out that 0. 1, 0, 1, 0, 0, 1 in base 2. So striking out that 0 gets you to this number. Same idea for going binary to hex and vice versa, except we're working in groups of 4. All right. And again, the idea here is if I have the lowest 4-digit binary number would be 0, 0, 0, 0, which in decimal form would be 0. The largest 4-digit binary number would be 1, 1, 1, 1. And again, to convert that to decimal, it would be 2 to the third, 2 to the second, 2 to the first, 2 to the first, geez Louise, 2 to the first, 2 to the 0th. So 8 times 1 is 8, 2 to the third is 8, plus 2 to the second is 4, times 1 is 4, 2 to the first times 1, so 2 times 1 is 2, and then 1 times 1 is 1. We're looking at 12, 13, 14, 15, all right? So the largest binary number, 4-digit binary number, converted into decimal form would be 15. And that's a total of 16 values. All right, and when we talked about hex, we said that we wanted only single characters. So 10, 11, 12, 13, 14, and 15 would be a problem. So we would do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then 10, 11, 12, 13, 14, 15. All right. F for 15 if you want to remember where to stop. So the way we handle converting over, I'll rewrite it down here. 1, 1, 1, 1, 0, 0, 1, 0, 0, 1 in base 2. All right, so we would break it into 4-unit clusters. This group here. I think I lost a place there. 1, 1, 0, 0, my not so great handwriting. 1, 0, 0, 1, 1, 1, 0, 0, and then, yeah, I think I got it right now. All right. Put a couple placeholder values in front. So our possibilities in terms of placeholder values, 2 to the third, 2 to the second, 2 to the first, and 2 to the 0th, which is the same as saying 8, 4, 2, and 1 across the board. So 8, 4, 2, 1, 8, 4, 2, 1. So converting that over, 0 plus 0 plus 2 plus 1 gets me a 3. Then for this piece, 8, sorry, put my little squiggly thing in the wrong spot. So 8 plus 4 plus 0 plus 0, which gets me a 12. All right, we'll handle that in a second. And then we have an 8. I did it again, squiggle in the wrong spot. 8 plus 0 plus 0 plus 1, which is a 9. Anything between 0 and 9 stands as is. But then anything 10 and above, so my 10 is A, my 11 is B, 12 would be C, 13, 14, and 15. So I'm looking at 3, C, 9 in base 16. All right. And so that's where this comes from. And going the other way is the same idea. All right. So, yeah, we have another example here going to base 16, same general process. But going the other way, if I have a 1, E, and A, so now I'm looking at hexadecimal to binary, 1, E, and A. All right. So E is the same as saying 14, because F is 15. A is a 10. All right. So I'll put that in parentheses or something. And if the numbers that I have available, if I'm going to binary, the numbers I have available are 8, 4, 2, and 1. I'm just thinking, how do I get to a 1? Well, I don't need an 8. Don't need a 4. Don't need a 2. All I need is a 1. If I want to get to a 14, again, working left to right, I want to get as many bigger numbers as I can involved. I'll definitely take an 8. If I take a 4, I'm up to 12. Then I need a 2, which will get me to a 14, but I wouldn't need anything else. And to get to a 10, I'll take an 8. If I take a 4, that's too much. It gets me to 12. I need to get to 10. If I take a 2, that gets me to 10, and then I'm there. So we're good to go. So in binary, this would be 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, 0. But then I would chop off those leading zeros. Don't need those placeholders. And I'd be left with 1, 1, 1, 1, 0, 1, 0, 1, 0, base 2. And that's what we get down here. All right. And you have a fun one that's made up of only non-numerical digits, but it's really the same idea. So BAD. So we're thinking, this is my 10. This would be 11. C would be 12, so D would be 13. And again, my possibilities are 8, 4, 2, and 1. So I'll take an 8. If I take a 4, that's too much. That'll get me to 12. I need to get to 11. So I'll take a 2. 8 plus 2 is 10. And one more will get me to 11. If 8 plus 2 will get me to a 10, then I already have A here, 1, 0, 1, 0. And to get to a 13, I'll take an 8 plus 4 will get me a 12. If I take 2 more, I'm at 14. That's no help there. So then I'll take a 1. And since this one actually leads with a 1, I keep the whole thing. I don't strike anything out. All right. So my binary number here would be 1, 0, 1, 1, 1, 0, 1, 0. 1101, again, base 2. All right, and so now you should be good to tackle 154.